AP Cram, Calculus AB, Free Response Exam Review, Question 3, Determining Critical Points. Water flow through a pipe. The rate at which rainwater flows into a drain pipe is modeled by the function r, where r of t is equivalent to 20 times the sine of t squared over 35 cubic feet per hour. T is measured in hours, and t is greater than or equivalent to 0 or less than or equivalent to 8 hours. The pipe is partially blocked as represented here, allowing water to drain out the other end at a rate modeled by d of t is equivalent to negative 0.04 t cubed plus 0.4 t squared plus 0.96 t cubic feet per hour. For t, again, is greater than or equal to 0 hours or less than or equivalent to 8 hours. Also, there are 30 cubic feet of water in the pipe at time t is equivalent to 0. At what time t, where again t is between 0 and 8 hours, is the amount of water in the pipe at a minimum? So when is it the least? Okay, justify your answer. I'll give you a moment to think and gather your thoughts about your strategy for solving this query. Okay, so again, you need to find at what time between t is greater than or equal to 0 hours or t is less than or equivalent to 8 hours at which the amount of water in the pipe is at a minimum. Okay, so this is the part of calculus I love, the part where you have actual application, because this is a real life question that occurs in many factories or maybe water treatment plants where they need to know low tide or low levels. So this does have practical application for those of you who are looking to enter the world of, I don't know, manufacturing or engineering or some allied profession in that area. Okay. So basically, okay, where do we start? What you're going to need to do is to set up an integral expression that expresses the minimum water level in the pipe, okay? So the first thing that I want you to remember is that we're told that there are 30 cubic feet of water in the pipe at time t equals 0. So that means, before anything enters, let's say the cutoff point is here and there, before anything starts flowing, there are already 30 cubic feet of water present in the pipe, okay? All right, so that's that. And next, you're going to set up your integral expression for the minimum. So the amount of water in the pipe at time t, our mystery time that we don't know yet, is going to be 30 because we can't necessarily get rid of it. We can, but this is how much we start with. So we have to incorporate it in order to correctly find out the minimum value, okay? So 30 plus the integral from 0 to t, RT dt, okay? I know it says Rx dx here, but it's really RT dt. All right, and so that's that. And remember that R of t equals 20 the sine of t squared over 35. I don't want you to forget. And d of t equals negative 0.4 t cubed plus 0.4 t squared plus 0.96 t. And when they ask you for a minimum, what they're really saying in terms of calculus and integration is we're looking for a critical point, all right? And you have to realize that an absolute minimum exists because you're working with a continuous function both of these functions are continuous. I don't have time to explain at length what that is because, we want these reviews to be as short as possible and they're already lengthy. So you'll have to Google that or tune in later to one of my other review snippets. So we need to look for the minimum. Okay, so this function has a minimum because it's continuous on a closed interval from 0 to t, and our closed interval is between 0 hours and 8 hours. So the function here that we're looking at meets those two criteria. Okay, so we have a critical value because it's a continuous function, and there are two endpoints. So you're expected to use your calculator again to solve for where the integral of r of t, not dt, minus dt is equivalent to 0. So if you input this integral, and again, I'm sorry for the x, I meant to write t but forgot. Just plot, first plot. I showed you in a previous video 3 in the series, how to plot a definite integral, or video 2, which is very similar, shows you how to plot an indefinite integral. Okay, so you need to plot this and then find out where r of t minus d of t is equivalent to 0. You need to trace it. Or if you plot the two graphs, you can find out where they're equivalent to each other, and you'll find out the time where they're equivalent to each other, and that's where you have a critical point, okay, or a relative minimum on the interval between 0 and 8 hours, okay? So after doing that, the integral, there should be an integral sign right here of r of t minus d of t, or r of t minus d of t is equivalent to 0. That means these two graphs are equivalent to each other at time 0 and also at time 3.271658 hours, okay? So at 0, they're equivalent to each other because nothing has flown yet. We start off with 30, but then we see that at time t is 3.271658 hours, there is a total of 27.96 4561 cubic feet of water in the pipe, okay? And to find out this answer, basically all you do is you take the definite integral from 0 to 3.271658 hours, and then it's going to give you this answer, okay? And just for good measure, we also use our endpoint at 8 hours, where it's 48.543686. This should be the relative maximum, okay? If they were asking at what time is the water at its maximum point, but that's not what we're looking for here. And again, just for good measure, in case you're wondering what a critical point is, it's points on a graph of a function where the derivative is 0 or the derivative does not exist, okay? And it has many applications, as we can see here, in determining the minimum water level in some type of pipe. All right. Okay, so just in case you're like, what the heck is she talking about? And I confused you on the previous flashcard, this is what your integral is supposed to look like. Here we have our starting amount at 30 cubic feet of water in the pipe. So 30 cubic feet of water at time 0. A 0 is supposed to be right here. and like a t, okay? So this is r of t, and this is going to be d of t. And we're deriving with respect to time because we're looking for an answer in terms of cubic feet of water, so we get rid of the dimension time, okay? And graphically, it's supposed to look like this visually. This is what your integral is supposed to be like. And as you can see, it's a continuous function, all right? And we're interested in this isolated a segment between 0 and 8, so right about here, okay? All right, and so we can see at 0, there's a point of inflection, meaning there's no change. The integral isn't changing, or you can see the derivative isn't changing. And there's also a point of inflection right here around 3.27, where the integral goes from decreasing to increasing, all right? So this is where our local minimum is. And around here, you can see that at about 8, so this is 1, 2, 3, it's at a high point of 40 point something, almost 50, okay? All right, so yeah, this is why our answer is around 3.27, because at 0, yeah, you know, the rate of change is 0, but here there's also like some of the water has been like ejected. Some of the initial 30 has been ejected, and it reaches a minimum here, a local minimum, because at like about, what is this, 13, we can see it's a little bit lower, but we're not interested in that, okay? Because again, our function is isolated between 0 and 8 hours and nothing more, nothing less. All right.